All right. At this point, we're going to introduce our an example of this induced electric field. Okay, we're not going to use a complicated loop like this. Rather, we're going to look at something very symmetrical to make your math easier. This is a circular E field. Okay, now imagine there is a circular electric field. It's produced by a magnetic field confined into a circular area. Those crosses are magnetic field lines pointing into the paper. Okay, it is contained within this circle of radius big R. Here is the center of that circle, point O. Okay, if there is a change in the magnetic field, so B changes. Let's say B is uniform, which means it doesn't vary from point to point within a circle, but it does change in unison. Okay, there's a rate dB dt. For definitive, let's say dB dt is positive. It's greater than 0. So you have a flux that's increasing into the paper. Okay. Now, as a result, there will be induced EMF, or we say induced electric field, right? I want to know what kind of induced EMF, what kind of induced electric field will be produced by this kind of changing magnetic flux. First of all, the flux is increasing, and nature doesn't like that. So what does it do? It tries to produce a flux that's up, right? That's against it, right? And that can only be produced by a current flowing counterclockwise. Okay, and because of the symmetry of the problem, everything should be symmetrical but point O, and therefore you can expect, if you put a circular circular metal wire here, centered here, there will be a current flowing through it. That's because there is a circular electric field going around to push it like this, right? So obviously you should be looking for circular electric field lines, which we never saw were possible before. We studied electrostatics only. Those, were you got radial lines, but you don't get circular loops like that. But now we have those circular electric field lines. Okay, so you can expect electric field lines like that. They're all concentric circles centered here. It's kind of like the magnetic field lines, okay, that you learned about, about a infinite long wire. So this is a new type of electric field lines. Okay, they will form, they will generate an EMF which would power a current if you had a real wire there. If I choose a radius R, what I want to know is, as a function of R, can you tell me the magnitude of these circular electric field lines? Okay, by symmetry, everywhere on the same circle, you have electric field lines. First of all, they're totally tangential, always, and they have the same magnitude. Okay, so we are going to use this formula, E dot ds, applied to any of these circular contours, okay, to find E. How do we do that? First of all, epsilon equals what? d phi by dt. Okay, we're looking at magnitude, so I'm going to ignore the negative sign here. So this really is the absolute value of epsilon. What's d phi by dt? It's ddt of what? The flux inside. The flux inside is just A times B. A is that area enclosed by the loop. Enclosed by the loop. Okay. B is the uniform magnetic field. So I can write this as B dA dt. I'm sorry, A dB dt. Okay. Because B changes but A doesn't. So A dB dt. A dB dt. What's A? A is pi r squared. Okay. Radius r. This radius from here to there is r. dB dt is whatever constant it is. Okay. That's given in the problem statement. So that's epsilon. But wait a minute, on the other hand, I know epsilon has equal to that. Let's elaborate on that a little bit. First of all, I know E and ds, they both form the same direction. That's tangential, so that's E ds. with cosine theta equal to 1. And secondly, E has the same magnitude everywhere on the circle. I'm going to take that E out. What's left is just ds. What's that? It's the circumference of the loop, which is 2 pi r. So it's 2 pi r times E. Okay? Equate these two, right? Equate these two. Pi r squared dB dt equals to 2 pi r E. Solve for E. E equals 2. Okay. R over 2 dB dt. Okay, this is the expression for the induced electric field. So you get a whirlpool like circling electric field. Okay, centered right here. They form circular loops, and the magnitude increases as you go out. It doesn't decrease; it actually increases. Okay, so it's somewhat like the magnetic field lines around a long current carrying loop, but not exactly the same because the electric field actually increases, not decreases. This is an example of an induced electric field due to changing magnetic flux. Okay, now to make things more interesting, okay, here's how I make things more interesting. I'm going to add a metal bar of length L from here to there. Okay, both of its ends would touch a point on the edge of the outer perimeter. So one is here, one is there. It's got a length L. Okay. By the way, this is radius big R. This radius big R, and this is also radius big R. Okay. Here's the thing. Then you vary the magnetic field, right, at this rate. As a result, there will be an induced electric field, and then this metal bar, even if it didn't move, okay, even if it didn't move, there would be a potential difference across its ends. You have just turned this thing into what? Into a temporary battery. In fact, if you connect this to a load, you're going to drive a current in the load. Okay? Now, my question is, what is the potential difference between these two ends? What is the EMF? Okay? On this metal bar. That's what I want to know. And which side is positive terminal, which side is negative terminal. I want to know that. Okay. How would I solve that problem? Well, first of all, let's determine which side is a higher potential, which side is a lower potential. Which side is, in other words, which side is considered as positive terminal, the other side is considered negative terminal. Here's the thing. You know the current, the electric field lines are like that, right? They will form counterclockwise circular loops. All right? So, if you look at a point here, any point on the bar, you can see, you know, the field lines will be, the electric field lines will be somewhat like this. Somewhat like this. So generally speaking, the electric field lines between here and there, generally speaking, they point from here to there, right? Point to the right. Of course, not exactly the right. They're also an up and down components, but they never point that way. Never point that way. So if you do this integral, okay? If you do this integral of E dot ds from the left end of the bar to the right end of the bar, from initial to final, you will get a potential difference, right? You get a potential difference. And E is generally pointing this way. It's generally pointing this way, right? So this will be the epsilon that you're looking for between the 2 points I and F, between the 2 points I and F, okay? And it is positive because generally speaking, E and ds, they're in the same direction. They both point towards right. What does that tell you? Which side is considered a positive terminal? Which side is considered as negative terminal? Now, normally you say, okay, if I follow the direction of the electric field, the potential would drop, right? You know, that's why a positive charge will always move from a higher potential to lower potential, right? Because it follows the direction of the electric field. But here, even though the electric field generally points from this I to that point F, I would say that point has a higher potential than this point. That point is positive terminal. This point, in fact, is negative terminal. Make sense? No? Well, let's see here. Let's look at a circuit. Okay, let's look at a circuit. A very simple circuit. Here's a resistor, and here's an EMF. Look at the direction of the electric field. it's like this, right? It's like this. Okay, that's how you power a current like that. Now, if you look at which end of this resistor has a higher potential, obviously it's this end, that end. So on the load, the potential gets lower if you follow the direction of the current or you follow the direction of the E field. Okay, you follow the direction of the E field, indeed the current, the potential drops. But look at what happens inside this battery. Inside the battery, the electric field points this way. That's how you push a positive particle from here to there, right? But you see, inside the battery, the electric field points from negative to positive, from low potential to higher potential. Instead of outside, it points from higher to lower potential. You have to note that difference. Okay, you have to note that difference. So this is effectively like a battery, or like a it's an EMF, right? It's effectively like a battery. So you can consider this as the interior of the battery, and within the battery, of course, the electric field points from lower to higher potential. You see? So that is why I consider that point positive and this point negative. Okay? That's what happens, and that is why if you connected this to a wire like this, a current like this will flow, which is of course expected. Now, next thing I want to know is, what is that EMF equal to? Okay, what is this integral equal to? What is this integral equal to? Well, you can calculate it directly, but it's gonna cost you some time. But because the thing is, between here and there, the electric field changes both magnitude and direction. Right? It changes from here to there. If I were to draw a more careful, it's like this here, and it's like this here, and it's like this here, and it's like this here, right? Because it has to go around in a circle. So therefore, E is variable. Okay, so is and the angle between E and ds also changes all the time. So you can do it, but it's not all that straightforward. Is there a better way for me to find this? Okay, it turns out, yes, there is. All I need to do is to apply the Faraday's law of induction to an appropriate area. I can apply Faraday's law of induction to any area of my choice. And what I want to do is I want to include this segment as part of that area, as part of the border of that area. Okay, over the entire area, if the contour around that area is C, then I have epsilon over the entire contour area, C, is E dot ds, right? That is only a part of that contour, but this is the entire contour. But according to Faraday's law, that's d phi by dt. Okay, for any contour, that d phi by dt is the rate of change of flux of the area enclosed by that contour C. You can use the entire contour like that, but you don't have to. Okay, I'm looking for this, which will be part of that integral, because that integral includes every segment, and this from here to there should be only part of that segment. Okay, so if I can choose a contour such that this integral is easier to calculate. See, if I use that as the contour, then the problem is you have to include the contribution from here to there over this very large arc. You can do that, but then you have to know the electric field there. You also have to know how long that arc length is. It's a little bit more geometry than we wish to handle, because there are easier ways to do it. Okay, can you think of an easy way? Look, the electric field lines are all tangential. But look at this radius. It's radial, right? Radial direction, tangential direction. What's the angle between them? 90 degrees. Okay, does that give you enough hint? What kind of area should you choose? Okay, how about if I choose what? This triangle. Look at this triangle. Okay, it's an isosceles triangle. Radius r and basis, radius r and the basis L. Okay, now if I follow this contour, 1, 2, 3, the integral will be the sum of 3 segments. 1, 2, 3, right? But going from here to there, what do you get? ds is like that, e is like that. What's the integral of e dot ds from here to there? 0, because e and ds are perpendicular to each other. Same thing happens when you go from here to there. Radially inward, tangential electric field. Okay, so there's no contribution to E dot ds for both this part and that part of the contour. The only thing left is from here to there, which is what you want. Okay, so this really is just equal to epsilon IF from here to there. How much is that equal to? That equals to d dt of the magnetic flux in the triangular area. Okay, in the triangular area, so it's A times B. All you have to do is find A. So it's dB dt times A. What's A? A is the triangular area. 1/2 base times height. Base is L. Height is that, which is the square root of r squared minus half of L squared. Okay, there we go. R squared minus half of L squared. See, you wonder how we can finish this thing in one step. It's because we made the best choice of a contour to apply Faraday's law of induction. We didn't have to worry about this segment. This segment, what's left is only the segment that we desire. Okay, so if you installed a metal bar here between here and there of length L, then there will be an induced EMF. The metal bar behaves like a battery, and that will be the EMF across the two terminals of the battery, with that end at a higher potential. Okay, we spent nearly 2 hours so far already on this lecture. Most lectures for each chapter is about 2 hours, but this is a particularly long chapter. It's got a lot of stuff going on, and we're not quite done yet. So we're going to go to a third part for this particular chapter. We're going to study further applications of the Faraday's law of induction, among which one of the most important ones, okay, that is, how do you make an electric generator? That is something that turns other form of energy into electrical energy, right? That's how we get, that's how we get electricity from a power plant. So what's going on in the electrical power plant? That's among the examples that we'll see in the third part of this lecture, which will come up.